Good morning, viewers. I am Thayalan from Radiological Physics Foundation. Today, we are going to talk about radiation units. Let us see first what is quantities and units. Quantities are necessary to estimate physical properties of a matter. For example, mass, length, and time are the quantities. They are all measured in kilo, meter, and seconds. The units are necessary to quantify them in a numerical scale for comparative purposes. Similarly, in radiological physics too, we have physical quantities and units. What is the aim of using the physical quantities and unit? This is to estimate the presence of ionizing radiation, energy transfer to the medium, and its biological effectiveness. International Commission on Radiological Units and Measurements, known as ICRU, started in 1928 to describe various quantities and units. What are the physical quantities we come across in radiology? Activity, exposure, karma, observed dose, equivalent dose, and effective dose. Whenever radiation travels in a medium, some physical properties are exhibited. What are the physical properties we come across to identify the radiation? Nuclear disintegration, ionizing photons presence in the medium, energy transferred from radiation, absorbed energy in the tissue. What is very important to describe unit? These physical quantities and their effect should have linear relationship between them. First, let us see what is activity. Activity refers to number of unstable nuclei present in a radionuclei. It is a measure of spontaneous nuclear transformation per second, that means disintegration rate. The amount of radiation released from the radioactive material is directly proportional to the activity. Therefore, activity gives an idea about the quantity of radiation released per second. What are the units of activity? Becquerel and Curie is the unit of activity. Becquerel came after the Henry Becquerel, who discovered radioactivity. Curie unit came after Marie Curie, who discovered radium. Becquerel is the SI unit and 1 Becquerel equal to 1 disintegration per second. Curie is a special unit which is equal to 3.7 into 10 power 10 disintegrations per second. That means 1 Curie is equal to 1 gram of radium-226, since radium is the first radioisotope used in medicine. Curie is a very big unit. Therefore, we use often millicurie, microcurie and nanocurie like that. What is 1 millicurie? 1 millicurie equal to 3.7 into 10 power 7 becquerel, which is equal to 37 megabecquerel. 1 microcurie equal to 3.7 into 10 power 4 becquerel, which is equal to 37 kilobecquerel. 1 nanocurie equal to 3.7 into 10 disintegration per second, which is equal to 37 becquerel. There is also one useful quantity. What is the relation between becquerel and Curie? We can deduce from this 1 becquerel equal to 1 divided by 3.7 into 10 power 10 Curie, which is equal to 0.27 into 10 power 10 Curie. Let us see the exposure quantity. Exposure indicates the amount of ionizing photons present in the field. Number of charged particles produced is directly proportional to ionization event. Hence, ionizing photons are quantified on the basis of total charge produced by them in the medium. What is the medium used? Air is the universal medium to measure exposure. The minimum average energy required is 35 electron volt to produce ionization in air medium. The quantity exposure expresses radiation intensity or strength or amount of radiation in a beam based on its ability to ionize air. Let us see the unit of exposure. The unit of exposure is Roentgen. named after the W.C. Roentgen who discovered X-ray. What is 1 Roentgen? Let us take 1 cc of air. 1 cc of air is equal to 0.001293 gram of mass. When you take 1 cc of air, you allow the radiation to pass. Then ionization takes place and charges are produced. How much ionization is produced? If the ionization is 2.08 in 10 power 9, it is called 1 electrostatic unit. So when the radiation passes through 1 cc of air, if the ionization is produced equal to 1 electrostatic unit, then it is called 1 Roentgen. That is why it is described as Roentgen is the unit defined as that of photons, which produces 1 electrostatic unit of charge in 1 cubic centimeter of dry air at standard temperature and pressure. What is important is, what is the SI unit of Roentgen? The SI unit of Roentgen is coulomb per kilo. Therefore, we can write 1 Roentgen equal to 2.58 into 10 power minus 4 coulomb per kilo, or 1 coulomb per kilo equal to 3881 Roentgen. So Roentgen is a very big unit. We often use milli-Roentgens in the clinical practice. Roentgen unit has some limitations. Roentgen is not a unit of dose nor the measure of instant flux of radiation. Secondary electrons may have long range. Measurement of their charge is a challenging one. Electron may escape the mass and does ionization outside the mass. It creates uncertainty in measurement. Roentgen can be used only up to photon energy of 3 MeV. It is defined only for X and gamma rays in air. Let us see what is karma. Karma stands for kinetic energy released in the media. When photon interact with an atom, it leads to absorption, scattering, Brunstall X-rays and delta rays. So, we can define the Roentgen as the sum of the initial kinetic energies of all charged particles liberated by the radiation in the material of mass 1 kilo. Let us see the slide. The photon is coming with h nu energy and interacting in an atom in a medium. Some part of the photon gets scattered in this direction. Some part of the photon is absorbed over a path length. During the path length, electron-electron interaction produces delta rays. If electron is stopped, it produces Brunstall. So the photon transfers kinetic energy initially at a point which is measured by karma, and later it appears absorbed energy along with the delta rays and Brunstall. So the absorbed dose over a path length, the green line indicate, are equal to kinetic energy minus Brunstall, provided the delta rays is very meager. What is the unit of karma? The unit of karma is gray, represented by Gy. 1 gray equal to 1 joule per kilogram. That means if we take 1 kilogram of substance of any matter, if the radiation energy absorbed is 1 joule, then it is defined as 1 gray. If the medium is air, it is called air karma. If the medium is tissue, it is called tissue karma. 1 air karma equal to 114 Roentgen, or we can write 1000 milligray equal to 114 Roentgen, or 1 Roentgen equal to 8.7 milligray, or approximately 10 milligray. Let us see observed dose. Observed dose measure the amount of radiation energy absorbed per unit mass of the medium. That means the observed dose is measured based on the energy absorption. Suppose if you say E is the energy absorbed, M is the mass of the medium, then E by M is equal to dose observed dose, or observed dose equal to karma minus Brunstall X-rays. The SI unit of observed dose is gray. 1 gray equal to 1 joule per kilo. Gray is a very big unit. Often we use centigrade in the radiotherapy or radiobiology. The special unit of observed dose is rad. Rad means radiation observed dose. 1 rad equal to 100 x per gram. That means if you take 1 gram of substance, if the energy absorbed is equal to 100x, it is called 1 rad. So we can find relation between gray and rad. 1 gray equal to 100 rad, or 1000 milligray equal to 100 rad, or 10 milligray equal to 1 rad. Very useful relationship in day-to-day practice is 1 milligray is equal to 100 millirad. Let us see F factor. Suppose if you know the exposure as X, then from the exposure one can calculate absorbed dose. So the absorbed dose equal to, you have to multiply with one factor called F factor into exposure. This F factor, F is called Roentgen to rad conversion factor. So in diagnostic radiology energies, the F factor is 1 for air, muscle, soft tissue. Therefore, the absorbed dose equal to exposure. Coming to the equivalent dose. Equivalent dose attempts to quantify the biological damage arising from deposition of ionizing radiation in tissues by different type of radiation. Suppose if the observed dose is D, then if you use a particular radiation, if you put a weighting factor for the radiation, the product of observed dose and weighting factor gives you the equivalent dose. Since we use different radiations, each radiation is having a separate LET value, that means linear energy transfer. We have low LET radiation, intermediate LET radiation and high LET radiation. Depending upon the LET, the radiation weighting factor varies. Therefore, the weighting factor multiplied with the observed dose gives the equivalent dose for the individuals. What is the unit of equivalent dose? Sievert is the unit of equivalent dose after the scientist named Sievert. 1 sievert equal to 100 rem. Rem stands for radiation equivalent men. Rem is a special unit. This slide shows the various weighting factors used for different type of radiation. Normally, we use photons. Photon consists of X-rays and gamma rays. The weighting factor is 1. So in that case, the absorbed dose equivalent to the equivalent dose. Electrons and muons, the weighting factor is 1. Protons and charged pions, the weighting factor is 2. Alpha particles, fission fragments and heavy ions, the weighting factor is 20. That means if you receive the same dose from gammas and alpha, alpha radiation is 20 times biologically giving greater impact than the gamma rays. In the case of neutron, the weighting factor depends upon the energy. It is a continuous curve as a function of neutron energy. Based on the energy, we have to assign the weighting factor. Coming to the effective dose. Effective dose is the product of equivalent dose and the tissue weighting factor. Suppose HT is the equivalent dose, then we have to multiply with the tissue weighting factor, then it gives you actually the effective dose. Since we have body is heterogeneous, we have multiple tissues, each tissues will have a different weighting factor. So we have to put the summation of the sum of all the weighting factor, that gives the effective dose. So WT refers the weighting factor of the tissue T exposed to radiation, and HT is the equivalent dose. So this can be simply written like that. This part gives the equivalent dose. So if you multiply with the WT, it gives the effective dose. So D is the observed dose in gray, WR is the radiation weighting factor, WT is the tissue weighting factor, the unit is sievert, special unit is rem, and 1 millisievert is equal to 100 millirem. The effective dose accounts the variation of LET as well as the tissue sensitivity. That means different organs having a different tissue sensitivity. So the effective dose address this issue for radiation protection purposes. As we told earlier, for gray, sievert is also a very big unit. We often use millisieverts in day-to-day practice. This slide shows the various weighting factors for the tissues. So bone marrow, colon, lung, stomach and breast will have weighting factor of 0.12 or 12% in the whole body. Gonad will have 0.08. Bladder, esophagus, liver, thyroid will have 0.04 each. Bone surface, brain, salivary gland, skin will have 0.01. Remainder tissues addressed here in the bottom will have 0.12. So therefore, if you have all the tissues taken as 1 for the whole body or 100%, so each tissue is given a weightage of similar. What we understand from this, the most sensitive organ in our body is bone marrow, colon, lung, stomach and breast. This slide tells you the relationship between the SI unit and non-SI unit. In the case of activity, Becquerel is the SI unit, Curie is the non-SI unit. Exposure, Coulomb per kilo is the SI unit, Roentgen is the non-SI unit. Similarly for air karma, Gray is the SI unit, Roentgen is the non-SI unit. Absorbed dose, Gray is the SI unit, RAD is the non-SI unit. Equivalent dose, Seward is the SI unit, REM is the non-SI unit. Effective dose, Seward is the SI unit, REM is the non-SI unit. To summarize, the radiation quantities we use: activity in Becquerel, exposure in Roentgen, karma in Gray, absorbed dose in Gray, equivalent dose in Seward, effective dose in Seward, Curie, RAD, REM are special units used often for activity, absorbed dose and effective dose. In practice, megabecquerel or millicurie, centigrade or rad, millisievert or millirem are also often used. The radiation quantities and units are useful to identify the presence of radiation, its quantity, energy transfer to tissue and its biological effects. I hope you enjoyed the video. Kindly subscribe and succeed. Thank you once again.